The shear force V is the resultant of shear stresses, which act vertically, parallel to the cross-section. We denote the shear stresses using the Greek letter tau. To maintain equilibrium, these vertical shear stresses have complementary horizontal shear stresses, which act between horizontal layers of the beam. One way to visualize these horizontal stresses is to consider a beam made up of several planks of wood. When a load is applied, there is a tendency for the planks to slide relative to one another. Now let's glue the planks together. When the load is applied, the planks cannot slide, and so horizontal stresses develop between them. If these shear stresses are larger than the shear strength of the glue bond, the glue will fail. These horizontal shear stresses don't exist if we apply a moment instead of a force, because that gives us a state of pure bending, and so there is no tendency for the planks to slide relative to one another. The presence of these horizontal shear stresses explains why wooden beams sometimes fail by splitting longitudinally. This failure usually occurs close to the neutral axis, for reasons which will soon be obvious. So how can we calculate the shear stresses? We can calculate the average shear stress acting on the cross-section as the shear force V divided by the cross-sectional area. But the shear stresses aren't distributed uniformly across the beam cross-section. The shear stress has to be zero at the free surfaces, at the top and bottom of the beam. So the average shear stress isn't very useful, since it doesn't tell us the maximum shear stress. Instead, we can use this equation to calculate the shear stresses acting on the cross-section. I won't cover the derivation of the equation here, but it's based on considering equilibrium of stresses acting on a small element within the beam. The equation assumes that the shear stress is constant across the width b of the cross-section, so tau is a function of the distance along the beam, x, and the distance above the neutral axis, y. V is the shear force acting on the cross-section, which varies with the distance along the beam. B is the width of the cross-section. It can vary with the distance y from the neutral axis, but in this case, the cross-section is rectangular, so B is constant. I is the area moment of inertia, which is a constant value calculated based on the shape of the cross-section. And Q is the first moment of area for the portion of the cross-section above the location we want to calculate the shear stress for. So it varies with the distance y above or below the neutral axis. It is equal to the product of the area above the location of interest, and the distance between the centroid of that area and the neutral axis. If the location of interest is below the neutral axis, we consider the area below the axis instead of the area above it. To calculate the first moment of area at this line, which is at a distance y from the neutral axis, we multiply the area of the blue rectangle above the line by the distance from the neutral axis to the centroid. Doing this calculation gives us an equation for Q as a function of the distance y from the neutral axis for a rectangular cross-section. And so we can obtain an equation which describes how the shear stress varies with distance from the neutral axis. The y term is squared, and so the shear stress varies parabolically over the height of the cross-section, with the maximum shear stress occurring at the neutral axis. This is opposite to the bending stress, which is zero at the neutral axis, and explains why the horizontal shear failure of a wooden beam we saw earlier occurs close to the neutral axis. By setting y to 0 in this equation, we obtain an equation for the maximum shear stress in rectangular cross-sections. It is equal to 1.5 times the average shear stress across the entire cross-section. The derivation of this equation for shear stress makes a few assumptions, so we need to be careful with how we apply it. First, it assumes that the shear stresses are constant across the width of the cross-section. For rectangular cross-sections, this is a reasonable assumption if the rectangle is thin. But for cross-sections like this one, the shear stresses can vary significantly over the width. And so, in these cases, the equation can really only give us the average shear stress across the width of the cross-section. It can't tell us what the maximum shear stress will be. Another assumption this equation makes is that the shear stresses are aligned with the y-axis. Shear stresses act tangentially at a free surface, so for a circular cross-section, for example, we can't strictly use this equation to get the distribution of shear stresses across the height of the cross-section. But we can still use it to estimate the shear stresses at the neutral axis, because the shear stresses there are aligned with the y-axis. The equation for shear stress at the neutral axis in a circular cross-section is similar to the equation for a rectangular section, where we have the average shear stress V over A multiplied by a constant. The constant is 4 over 3 for a circular cross-section and 3 over 2 for a rectangular one. We can also use the shear stress equation for thin-walled sections like this I-beam, although things are a bit more complicated. Because the vertical shear stresses at the surfaces shown in red must be 0, and because the flanges are very wide, the vertical shear stress in the flanges is very small. This means that the vertical shear stress is distributed like this. The web mostly carries the shear force, and the flanges mostly carry the bending moment, as we saw earlier. You can see that the shear stresses are distributed quite evenly over the height of the web. This is because the flanges contribute significantly to the first moment of area Q when calculating the shear stresses in the web, but they don't carry much of the vertical shear force. Since the web is thin, the shear stresses are also distributed evenly across its width. Because of this, we can easily calculate the approximate shear stress in the web, like this. More detailed analysis reveals that there are shear stresses in the flanges, but they are acting mainly in the horizontal direction. The horizontal stresses on both sides of the flanges cancel each other out, so the net shear force is still just a vertical force. We can figure out the direction of the horizontal shear stresses based on the direction of the vertical shear stresses by imagining that the stresses are flowing through the cross-section. That's it for this review of bending and shear stress.